So when we talk about the history of knowing that there's an atom, I'm not sure that you can completely put yourself in the shoes of somebody living 1,000 years ago, 5,000 years ago, 10,000 years ago. What is all this stuff made of? You have no evidence. You don't have much of a way of gathering evidence. You can make stuff up. That's a possibility. But you don't have any body of knowledge to look at. And we really take the body of knowledge that we've got for granted. You know, there are things that you've known since the 3rd grade. Well, everybody knows that. Well, they didn't always. It all starts someplace. So that's what we're looking at. And if we start out with the Greeks. So here we're talking, Democritus is the first Greek we're going to talk about. He lived, roughly order of magnitude, 400 years before Common Era. That's the phrase that's used in a lot of science to describe what was the old BC AD, because those specifically refer to events within the Christian calendar, and the whole world doesn't use that. You know, that's pretty meaningless in a place that doesn't have that as part of their history. So we use before Common Era, because the Common Era is what we would otherwise call AD. So we use BCE and CE. Okay, so Democritus is not a scientist in the sense that we think of a scientist. He is a scientist in the sense that the Greeks thought of as scientists, which really is more akin to what we would call a philosopher. He's asking questions about the nature of being and the nature of matter and the meaning of life and the meaning of stuff. He's not using tools to discover these things. He's not going through anything that we would recognize as a scientific process. Most of what he's doing are what we would call thought experiments. Well, if you imagine this, well then what would happen if you did this? That's a thought experiment. Einstein was great at thought experiments. We'll talk about Uncle Albert and his thought experiments later. So Democritus is thinking about what makes up stuff. Because it's a pretty big question. Everything around us is made up of something. Well, if I cut this desk in half, are the 2 halves still a desk? Are they parts of a desk? And Democritus, and I believe he actually talked about it with gold. And I think he actually imagined this with gold. That if you took a lump of gold and you cut it in half, now you have 2 lumps of gold. And if you take one of those and you cut it in half, now you have 2 smaller lumps of gold, and you take one of those and you cut it in half and you get 2 smaller lumps, and you can go all the way down. And he thought that there must be some point you would reach where the little lump couldn't be divided anymore. There would be some point where this indivisible thing arose. Now, he called that atomos, which is derived from the Greek word for indivisible. His ideas about atoms were nothing that you would recognize. He posited that these little atomos would have all these different shapes. There were, and I've seen images of, and they had like little hooks and barbs on them, like Velcro, and that's how they held together. And, you would have atoms of water would have one characteristic. Well, we don't, that sounds really weird to us as moderns who have the benefit of all this knowledge. Different shapes, different sizes. He figured they were probably indestructible, that once you got down to this initial indivisible unit, they couldn't be destroyed, they couldn't be moved. So he had some stuff that sounds pretty crazy to us, but foundationally, just the idea that there was something that couldn't be divided, that's really big. That's really a big idea. So Democritus has some good ideas. And then along comes Aristotle. So Aristotle comes after Democritus. Don't forget that in the BCE, the numbers run backwards because we're counting up to 0. But how did they put the date on things? They didn't know when 0 was going to happen. That's a joke. They were using other calendar forms. So Aristotle, and the work of Democritus and his students, there would have been, in Greece, there would have been schools of thought. So you can imagine these philosophers sitting around discussing things. So we talk about like Platonic thought. Plato was Aristotle's teacher. So you have the Platonic school and the Aristotelian school, and Democritus comes before those guys. Democritus and the people who believed what he was saying, who agreed that he must be onto something, were the atomists. And Aristotle, who is also thinking about, what is all this stuff made of? What's it made of? What composes the world that we see? He says, no. There is no indivisible unit. All matter is this continuous spectrum of stuff. And if you go into, I actually have a couple times, every year I go back and I try to read Aristotle's, it's like Discourse on Form and Function, or Form and Matter, and he talks about things like, a table has two aspects. It has, which comprise its tableness. It has its form and it has its substance. And he goes into all this stuff, and it's really bizarre sounding stuff to us, and it sounds kind of like gobbledygook and voodoo. Really, he breaks it down into, you are composed of 4, and some sources say 5, because you have the ether, air, earth, air, wind, and fire, plus this 5th, which is spirit or ether, and this comprises all things. And a table is made of some number of parts earth and some number of parts something else. I don't know. It makes no sense to me as a modern person who has an understanding of atomic theory. But it apparently fit in with some other parts of the worldview of a lot of people at that point, because people, well, and also I think Aristotle was probably a better publicist. That whole sort of like self-promotion thing, I think he did pretty well, because we talk about Aristotle a lot more than we talk about Democritus. So Aristotle kind of holds sway, and people really kind of dismiss all that crazy nonsense about indivisible pieces. And so we have, the learned people of the period who come after this. Are you a man of learning? Well, surely you've read the works of Aristotle on form and function, on substance and matter. Surely you understand what Aristotle has to say. And this is the view. This is the perspective. So Aristotle's stuff, the root ideas he's got, these crazy ideas about, earth and air and wind and fire that make up desks and tables and trees and people, are picked up and are carried. And we have the rise of something that's called alchemy. So alchemy is this, again, it's more of a philosophical system. And alchemy uses those Aristotelian ideas about matter, that matter is comprised of the 4 elements. Some matter is imbued with ether, with spirit. Alchemists have this belief, for instance, they believe that metals are all made of, sulfur and gold, and that by removing the sulfur you can get to the gold. So this whole idea of they want to transmute, the stereotype is the alchemists were just interested in turning everything into gold. That's what they wanted to do. Lump of coal, I can turn that into gold. Lump of lead, I can turn that into gold. You got some iron for me? I can turn that into gold. Okay, what you got? What you got? Gold, gold, gold. And it was a little bit more complicated than that. So they were working from these ideas from Aristotle about things being comprised of various elements, not elements in the sense that we use the term. They were looking at combinations of things, making up other things. Now, when you say it that way, it doesn't sound so crazy to us, does it? The things that they thought were combined were a little bit wackier. The one school of thought is that, alchemy was really just magic and voodoo, crazy people in dungeons. There are a lot of people now who say, well, yeah, but. And there were a couple, I think they were like chem profs, I forget where, who actually looked through old alchemical writings and looked at the diagrams and the pictures and tried to replicate the laboratory equipment and found that, oh, hey, this stuff is kind of workable, and it's also kind of the forerunner of a lot of stuff we use in the lab today. It's the alchemists who actually give us things like distillation. They worked with distillation a lot. So the distillation equipment that we have here in this lab, which we never use, is actually kind of derived from a lot of things that were developed in these, what we at one point would have dismissed as just these, these whack jobs basements who were playing with glass and lead and gold and mercury. So anyway, this is sort of a school of thought and an approach to what some people would say is protochemistry that goes on for a long time. So, from before the Common Era, well up through the Dark Ages, up to the cusp of comes after the Dark Ages? Well, I was going for Renaissance, but yeah, it's all kind of tied in. So you have this period of time when not a lot of new deep thought is going on, and then you have this explosion, this flowering. And it's not just art, and it's not just poetry, and it's not just writing, and it's not just architecture. It's science, too. So the Renaissance, when we talk about somebody being a Renaissance, it's usually said Renaissance man. I prefer Renaissance person. Well, you're quite the little Renaissance person, aren't you? We're talking about somebody who is sort of equally interested and equally gifted in a broad variety of subjects, because the Renaissance encompasses all of that. But before we can get to the Renaissance, we got to trudge through the Dark Ages. So we've got these crazy, wacky ideas of Aristotle's, and time is passing. Civilizations rise and fall. Yeah, it's a lot of time. It really is. It's a lot of time. And nothing is really changing in science. We're not doing anything great. We're not thinking about atoms. We're not questioning these wacky ideas of Aristotle's. We're just kind of trudging along, doing the same old thing. Like 1,500 years of the same thing, more or less. So sad. Not thinking about atoms. That Democritus, his stuff is lost. Lost to history. Not really exploring any of these ideas about matter in anything that we would call a scientific method. Then, this is where we get to the Renaissance. And actually, this is the Renaissance. I'm not a historian. I'd have to look up dates for when people say the Renaissance starts. But what happens in the late 1700s, which is the 18th century, I always screw that up. In the late 18th century, we have what's called the Chemical Revolution. And you probably ran across the name Anton Lavoisier. Lavoisier, thank you. My French is atrocious. So Lavoisier is typically, he's sort of a figure at the center of a lot of this. But you also see names like Priestley sometimes. Avogadro pops up from time to time towards the end of this period. What's happening is suddenly there's this big interest, this big boom in quantitative chemistry. So what kind of chemistry are we talking about if we're talking about quantitative chemistry? Chemistry that involves numbers. And this is like heavy-duty measurement. So there had been this wacky idea, and I can never pronounce it correctly, flagellistic. It's a PHO something, like, but there's an L in there someplace. Anyway. And this was an idea that came out of the alchemists and Aristotelian ideas that like if you burn a metal, if you take a chunk of magnesium and you burn it, it weighs more when you're done burning it than it did before. No. Yes. Yes. Well, so the supposition of the wacky alchemists was that metals were made of something else plus this flagella blah 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 stuff, and it just has a negative weight. That's it. When you burn it, you just get rid of the negative weight, and then it weighs more. Yeah, that seems reasonable, right? Yeah, I think that works. Okay, good. You're all good with that? Excellent. Yeah, Lavoisier comes along and says, that's ridiculous. So he does a lot of work, and Priestley does a lot of work, and Avogadro kind of comes in on the end of some of this. there are really a lot of people doing a lot of work, and understand that at this point, these are not the people we think of as chemists. I mean, Lavoisier is considered the father of chemistry, of modern chemistry, and gives us a lot. But a lot of the people who are doing this kind of work, I always describe them as rich white guys working in the basement. This is happening in Europe, and the people who have, number one, the luxury of being educated are wealthy or have wealthy patrons. So do you know what a patron is? Someone who funds you for your work. Ms. Carcella, I really like your thinking and I really like the work you're doing on this and this and this. Let me just give you this many dollars per year so that you can continue your interesting work. And in exchange, you'll talk about how wonderful I am. Patrons. So there was this big patronage system. But mostly, yeah, we got a lot of rich white guys playing around in their basements. And this is happening in France. This is happening in England. You don't hear of a lot of Germans at this point. Of course, Avogadro is Italian. So this is a European phenomena, primarily. And we have lots of people taking measurements, and lots of people doing careful work, and lots of people writing papers, which they then share with one another, which causes them to ask questions. That's a good thing. All of this work and all of these observations lead to 3 laws. Now, let's clear up something here. A law is not a theory that did a good job, okay? A law is not a theory that got a gold star on its forehead. A law doesn't explain anything. A law explains nothing. I'll give you an example. Law of gravitational attraction. Newton. There's a wacky guy. Law of gravitational attraction explains nothing. It describes what happens. It describes it very well. But laws don't explain. They just describe. And as a visual learner, I'm picturing a little person who's labeled, law of the natural world, saying, look, I don't have to explain anything to you. That's the visual image I have. Like somebody being a little bit confrontational. I don't have to explain anything to you. Laws don't explain. They just describe. They're descriptive. So all these people are taking all these measurements, and these measurements lead them to describe what they're seeing. They don't know why. They don't know why they're seeing what they're seeing. They can't explain it yet. So let's look at these laws independently. Okay, law of conservation of mass. You're very familiar with this. You learned about it in physical science. You probably heard about it before then. In an ordinary chemical reaction, yeah, I think this is kind of funny. In an ordinary chemical reaction, we can't destroy or create mass. Can't do it. We don't get rid of mass in chemical reactions. So, one of the things that led to the explanation, the dismissal of the flagello blah 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 istic combustion theory, if you take a set of chemicals in a sealed container, no air can get in or out, and you run a reaction, the mass of the container beforehand is equal to the mass of the container afterwards. So if there's no way for anything to leave or enter the container, the mass doesn't change. Mass of the products is equal to mass of the reactants. Some kind of chemical reaction happens, but the mass doesn't change. So this is law of conservation of mass. This is the easiest one of these to understand. If I give you vinegar and baking soda in a sealed container, in some sort of capsule, seal it up, and you shake it so that they begin to interact, it's going to have the same mass before and after, as long as it's a sealed container, as long as nothing can escape. So this one's easy. Definite proportion. This one's not too hard. If we take, now we understand the basis for this now. It was not understood at the time. If we take the results of, so let's say we burn that chunk of magnesium. Okay, nice and bright, nice and hot. Get out your marshmallows, we're ready to toast them. 4,000 degrees, woohoo! Those are some toasty marshmallows. So if we take a bunch of samples of magnesium and we combust them all in these sealed chambers, And then we are able to somehow break this apart again. We're going to find that every time, no matter where it's from, we have the same percentage of oxygen and the same percentage of magnesium. You have the same percentage of pure metal and the same percentage of oxygen. And it's actually around this time that they figure out that there is such a thing as oxygen, that there's this gas that combines with metals. This is part of the whole dismissal of the early combustion theory. So no matter where we get the magnesium oxide from, no matter how much of it we look at, the proportions are always the same. Okay, that's positive. We don't know why. We have no clue why. But they're always the same. Okay, we're not explaining anything, we're just describing. That's law of definite proportions. Now the weirdest one, the one everybody hates, is the law of multiple proportions. So let's just read this together, shall we, and see how much sense it makes. If two or more different compounds are composed of the same two elements, then the ratio of the masses of the second element combined with a certain mass of the first element is always a ratio of small whole numbers, huh? That's incomprehensible. And this is the one, honestly, coming into teaching this stuff, minor in chemistry, I never understood this. A lot of college chemistry, never understood this. I don't expect that you'll walk out of here and be able to explain this to somebody on the street who you find randomly. Hey, have you heard about the law of multiple proportions? Can I explain it to you, friend? It's like chemistry evangelism of some sort. I don't know what, but walking out and sharing the good news about multiple proportions. Don't try it. Don't try it. Nobody will like it. Nobody will like it. So, to explain this in slightly easier to understand terms, if you have CO and CO2, now of course we understand that these are made up of atoms of carbon and atoms of oxygen. They didn't, but they were able to separate and measure these things, and I'm going to tell you honestly, I don't know how they did that. I really don't. I do not understand how, without a knowledge of atoms, because it's so hard to put yourself in the place of not knowing something that you know as foundational. I don't know how they were able to separate these things, but apparently they were. So you can observe this. You've got CO, you have roughly 12 grams of carbon and 16 grams of oxygen. CO2, you got roughly 12 grams of carbon, but you have 32 grams of oxygen. Well, if you look at the ratio of oxygen, that's 2 to 1. And I think it was Lavoisier who did this work. And I'd have to look it up again. He was actually working with methane, which was known as swamp gas, which is CH4, and ethane, which is often called natural gas. That's got 2 carbons and 4 hydrogens. So we've got those simple small whole number ratios. So what he saw, though, was that you keep popping up with things like 2 to 1, 3 to 2, 2 to 4, which is, of course, 1 to 2. You keep getting these small whole number ratios, and that never changes. And this started to suggest that there were pieces of these things, that you can only have a piece of oxygen. Does that make sense? I'm not concerned that you understand how law of multiple proportions works. Like I said, it is the weirdest one of them. It's the most confusing to most people. But what's important isn't as much these laws, which remember, don't explain anything, as what someone used them as the basis for. So we get old John Dalton. He's a school teacher. He is a school teacher. And he's a chemist. He's, I guess, sort of a hobby chemist. And I don't know that Dalton, I mean, he would have not been, somebody whose family had been in a debtor's prison, obviously. He had something behind him to allow him to become educated enough to be a school teacher. I don't know if he had a good patron or what, but Dalton looks at those laws and says, you know what? I think I can explain those. So the laws themselves don't explain anything. They just observe. But Dalton says, I think I can come up with an explanation that would fit all of those laws. So number one, there are these little tiny pieces that everything is made of. Those are the pieces. And he calls them atoms. He's going back to Democritus' word atomos. That's where he's getting that word from. And he thinks that there are different atoms of different elements. that there would be gold atoms, and that there would be silver atoms, and that there would be carbon and oxygen atoms and hydrogen atoms. And he thinks that if you've got an atom of gold, it's going to be the same as every other atom of gold there is. He's not too far off, maybe. And he also says that you can't create, destroy, or divide an atom. They are indivisible. They are at the bottom. These are the first 3 points of Dalton's atomic, and I suppose if we're going to be technical, it would have really been an atomic hypothesis. But repeated observations over the last couple hundred years, nothing has shot a hole in this. You know, we call it Dalton's atomic theory. But there are 2 more points to Dalton's atomic theory. And we can all buy these as moderns who know a little bit about chemistry. We can take atoms of different elements, we can put them together, they form compounds. And when we do a chemical reaction, we just switch dance partners. They rearrange themselves to form new stuff. So of those 5, does anybody have a problem with any of them? As a modern person who has a knowledge of chemistry. Well, there are 2 problems with them that we know about now. One is that we do know that there are pieces smaller than the atom, and that was figured out. So the two modifications that we make to Dalton pretty quickly in the next 100 years or so. Number 1, there are pieces that are smaller than the atom. And you know those, and these are the things you've known since the 7th grade. 6th grade, 5th grade, 4th grade, I don't know. Yeah, protons, neutrons, electrons, sure, they're smaller than the atom. We can divide the atom. But if we break it up, like if we lose protons, it's no longer an atom of gold, or it's no longer an atom of uranium, or it's no longer an atom of aluminum. It's something different. And the other thing that Dalton wasn't aware of is the proton and the fact that you can have different atoms of gold that have different masses. So he didn't understand isotopes. And that's pretty minor when you think about it, to miss those 2 things, to think that he was coming from really almost nothing and pulling together something that explained those laws. So we're going to pause here with Dalton